Hi, my name is Brian Caffo, and this is the lecture on least squares estimation of regression lines in the Regression Coursera course as part of our data science track. My name is Brian Caffo, and this course is co-taught with Jeff Leek and Roger Peng. We are all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so hopefully you've watched the previous lectures and where we've kind of gone over some of the basics and then also gone over notation. Let's consider the parent and child data sets again from Galton. And here it is. We'll remember the size of the circle represents the number of points at that particular XY combination. And now we would like to fit a regression line through that data, so a line that in some sense is the best line through the data. And that's what we're going to talk about today, and we're going to talk about doing it with least squares. So let's let yi be the ith child height and xi be the ith parent's height, which is the average with the correction that we talked about previously. And we'd like to use parent's height to predict children's height. And so we're going to try and do it with a line. Child's height is beta naught plus parent's height times beta 1. And to find that line, why don't we use so-called least squares? So what we'd like to do is, if this was the regression line, remember that the regression, a line only takes two parameters to describe, a slope and an intercept. And so if we had that regression line, if we were to plug in, say, a child height, xi, and multiply it times the slope, beta 1, and add the intercept to it, beta naught, then we would get the predicted, if we were to take a parent's height, xi, and multiply it times the slope, beta 1, and add the intercept to it, beta naught, then that would give us a predicted child's height based on the regression line. Yi, in contrast, would be the actual child's height, not based on the regression line, the one that was actually recorded. So the difference between these two is the difference between what the model would predict for that child and what actually was observed for that child. And so why don't we, as a criteria for the best line, minimize the sum of those squared distances? In a pictorial sense, that is, if we have a bunch of data points like this, right? That's trying to fit the best line through the data that minimizes, this is that distance. This would be yi, and this point right here would be beta naught plus beta 1 xi. And we want to minimize the sum of these squared vertical distances. And we square them, of course, so that we have always positive things, so that being a certain distance below the line is equivalent to being a certain distance above the line, the same distance above the line. So how do we do it? Well, I'm going to, again, so if you're not interested in the mathematics, the homework questions and the quiz questions won't focus on the mathematics. So this is, again, right now, only if you're interested in the details. If you're not, you can skip ahead a couple of slides. But I'm going to go through all the details again without requiring calculus or linear algebra. So let me let mu be beta naught, mu I be beta naught plus beta 1 xi, just to reduce some notation. Then our estimate would be mu I hat if we found a specific value of beta naught hat, and a specific value of beta 1 hat, then our fitted mean would be mu I hat for that pair. Okay, so we want to minimize yi minus mu I, where I've just now replaced, in the previous equation, replaced the beta naught plus beta 1 xi now with mu I. We want to minimize the sum of yi minus mu I squared. Well, why don't we add and subtract like we did with the mean when we didn't have a regression line, we just wanted to do the mean. Why don't we add and subtract a mu I hat and then expand that square, and we get this set of equations right here. And if this term right here is 0, in other words, if this term right here is 0, then then we wind up with this equation right here. But notice this is the sum of a bunch of squared things. Squared things have to be positive, so if we discard this, we only get bigger. So the end result is we'll find the best mu I. If that condition is met, then the mu I hat that we come up with will be the best one. And we're only going to search among mu i's that satisfy this criteria, that they are beta naught plus beta 1 xi. We would get a different mu I if we allowed the mu I to have a different criteria. Say if we added another one, beta 1 xi plus beta 2 zi or something like that, we would get maybe a better fit. But right now we're only going to do it with the single line. Okay, and so the key is if we can make that condition, and the reason I do it is because we'll just use that condition in all the different ways we develop regression later on. We just note that that condition has to happen, and then if we can find something that satisfies that condition, then we will have found the least squares estimates. Okay, so just to recap here, if this criteria is met, where mu I is this and mu I hat is the fitted values, then the regression line y equal beta naught hat plus beta 1 hat x, that line is the least squares line. If we force beta 1 to be 0, then we only have the one parameter, beta naught. And then it's only considering horizontal lines, and that works out to be y bar. We already worked out the solution, right? We want to, if you just want to minimize yi minus beta naught quantity squared, we've already worked out that solution in the previous lecture. But let's show it again, just to remind us. Well, I'm sorry, we worked it out in the previous lecture, but why don't we just show that that meets that criteria? Okay, so here's the criteria that we said has to be equal to 0 to get the regression line. Let's plug in our beta naught hat. So here we've converted, in this case, mu I hat to beta naught hat and mu I to just beta naught. And this term doesn't depend on I, so we can pull it out of the sum. And we get this sum right here. And that will equal 0, just expanding it out, if ny bar minus n beta naught equals 0 right there, and then solve that for beta naught hat, you get beta naught hat equals y bar. So exactly like we did it previously, when we previously developed these same equations, only now we've kind of created a somewhat automated way of doing it. We just have to figure out, parameterize our mean mu I hat, and then show that equation equals 0, and then we've got it. So it gives us more of a constructive way to do it rather than before when we had a sort of trick. Okay, so now let's do regression through the origin. Okay, so here, remember, we need to have this equation be equal to 0, and where mu I is this and mu I hat is that, and then this guy will be the regression line. If now, instead of forcing beta 1 to be 0, if we force beta naught to be 0, right, then we will have a regression line through the origin. Okay? And in this case, the solution works out to be beta 1 hat is the inner product of y and x divided by the inner product of x by itself. If you're used to that sort of notation, but it works out to be that, and it'll make a little bit more sense when we include an origin. Okay, but let's just show that this works out to be the case. Okay, here's the criteria that we have to meet. I want my pen, not the square. I get it. There we go. There's a pen. This is the criteria that we need to be 0, and here we've parameterized mu I to be equal to beta 1 xi. Okay, so plugging in our beta 1 xi and mu I hat as beta 1 xi hat, so we get this equation right here, just plugging in. Then factoring out the xi, right? We can factor out an xi here, Okay, there we've factored out an xi. Then we have a beta 1 hat minus beta 1, and that can get pulled out of the sum, and the xi can get brought into that sum, so we wind up with this equation right here. So this, if that equals 0, then this will equal 0, okay? And so this will equal 0 if that equals 0. Expanding it out and solving yields the equation that we said was right. So let's recap what we know. If we define mu I as beta naught, then beta naught hat works out to be y bar. So if we only look at horizontal lines, the least squares estimate of the intercept is that line that's the average of the outcomes, which makes sense, right? We're disregarding x then. If we look at regression through the origin, then the line, the slope of that line works out to be that guy. What about when we have a intercept and a slope? That is, we don't restrict ourselves to horizontal lines or lines through the origins. That's when we get to real regression. Let's figure it out. Okay, so remember we need that to be equal to 0. So let's plug in beta naught and beta 1. So we're here, our mu I is equal to beta naught plus beta 1 xi, and mu I hat is just equal to beta naught hat plus beta 1 hat xi. Okay, so if we plug in, we get this equation right here, and we can pull the beta naught hat minus beta, group them together, and get that equation and that equation. Okay, and so if that guy is 0 and that guy is 0, and I'm sorry, that guy is 0, then we're set. Well, let's look at this one first. So that yields two equations, two unknowns, right? So we should be able to solve it. Okay, well, let's look at that one first. And if you solve that, if you expand the sum, we get that ny bar minus n beta naught minus n beta 1 hat x bar, and this implies that beta naught hat equals y bar minus beta 1 x bar. So now we can then plug this solution for beta naught into this other equation. Okay, and so if we to set that one equal to 0, and so here I have it rewritten down there where I've then taken my beta naught and plugged in that equation right there. Okay, let's continue on to the next page. And this has a nice simple form. It's the centered y's minus beta 1 times the centered x's, and it appears like very similar to our regression through the origin equation. So then we can solve this. We get summation yi minus y bar times xi minus beta 1 summation xi minus x bar times xi equals 0. Beta 1 is what we want to solve for. We just solve and we get this guy right here. The beta 1 is the summation of yi minus y bar times xi divided by the summation of xi minus x bar times xi. Now, let me just note that summation of yi minus y bar times x bar is equal to the average, because x bar doesn't depend on yi minus y bar right there. But this is the sum of the deviations around a mean. But we already know that to be 0, right? We already know when we center random variables, their resulting mean is 0. So if we were to take this xi right here and this xi right here, and the same is true whether this was yi minus y bar or xi minus x bar, we can subtract off, we can turn it into xi minus x bar instead of just xi in each case, because then if we multiply the sum through, it is equal to 0, right? That part's equal to 0. Okay, and the nice thing about that is then this quantity right here, we could divide it by both of them. We could divide it by n minus 1 in the numerator and n minus 1 in the denominator, and we haven't done anything. We've multiplied by 1. And then what we see is that this works out to be the correlation of y and x times the standard deviation of y over the standard deviation of x. And this is the sort of famous formula, that the slope of the regression line is the correlation, the empirical correlation, times the ratio of the standard deviations. And then, of course, recall that the beta naught, the intercept, it works out to be y bar minus beta 1 x bar. This, by the way, guarantees that our regression line always travels through the average of the point that is x bar, y bar. Our regression line always travels through that point, which is interesting and kind of good in that we would expect it to be the case, that the line would travel through the exact middle of the data. Okay. Get that again. Okay, so the least squares model fit to the line, to that line right here. Let me see, to that line right here, through the data points xi as the outcome. It works out to be, notationally, we call it y equal beta naught hat plus beta 1 hat x, and it works out where the slope is that guy right there, and the intercept is that guy right there. Okay, and the slope has this famous formula that it's the correlation times the ratio of the standard deviations. Notice, by the way, the units work out right. So the correlation, right, that has units of y times units of x, right? And this has units of y, and this has units, I'm sorry, let me try again. The correlation is between minus 1 and plus 1 is a unit-free quantity. This guy has units of y, this guy has units of x, so the units of the slope are units of y over units of x, which makes sense, right? The slope is the change in y over the change in x, so it has to have those units. Okay, so there we go. Beta 1 has the units of y over x. Beta naught has units of y, of course. The line passes through the point x bar, y bar. You can double check that just by plugging in if you'd like. And the slope of the regression line, just if you were to reverse y and x, is set x is the outcome and y is the predictor. Well, it's pretty clear what would happen. You would wind up with the same correlation times, instead of standard deviation of y of standard deviation of x, you would multiply it times standard deviation of x over standard deviation of y. It's also neat that how important regression to the origin is. If we had simply centered our data, forced it to go through the mean of the data by centering the x's and centering the y's, and did regression to the origin, all right, got an intercept, then you get the same slope, right? Which that makes a lot of sense, right? So if we don't fix the intercept, we get a regression line that goes through the average of the y's and the average of the x's, and we get a specific slope. If you go ahead and center the data so that the origin is the means of the y's and the x's, then and do regression to the origin, then you get the same slope. Okay, that makes great sense, and of course that works out. If you normalize the data, don't just center it, but then also scale it so that it has both mean 1 and variance 1, mean 0 and variance 1, excuse me. Then your regression slope is nothing other than the correlation, right? Because the resulting centered and scaled random variables, they have slope. I'm sorry. Then their standard deviation is 1, so the formula would work out to just be the correlation. Okay, so let's revisit Galton's data. In this case, just to not have to keep typing the $, why don't I just define y and x, and then our beta is the correlation of y and x times the standard deviation of y over standard deviation of x. And our beta naught is mean y minus beta 1 mean x, okay? And then we could spit those out, right? And just to double check myself, I'm going to grab the coefficients from the R program LM, which does exactly regression, y tilde x, and you can see, of course, that they work out, of course, to be the same. So I didn't mess up my math. Again, I wanted to illustrate that if you reverse the predictor outcome relationship, that just all you got to do is flip the standard deviations. So our beta 1 now is going to be standard deviation of x divided by standard deviation of y. Beta naught is this guy. And then here now, instead of, I'm going to compare them to the coefficients I get. Instead of y tilde x, I'm going to do x tilde y, where x is treated as the outcome, and of course they agree again. And then let me point out this last point. Regression to the origin yields an equivalent slope if you center the data first. So why don't I define y-centered as y minus the mean of y, x-centered as x minus the mean of x. I'm going to take my beta 1 as my regression through the origin slope, which, remember, regression through the origin was just summation yi times xi divided by summation xi squared, which is what that quantity is right there. And then let me get my I'm going to compare my slope, beta 1, 0.64, and I'm going to compare it with the coefficient if I included an intercept, which again is 0.64. You see, so the regression through the origin slope, having centered the data, is exactly the same as the slope as you get if you were to fit an intercept and not demean the data first.